Hey everyone, it's Jim
And Charles
from Mellow amps, and in MTA episode 21 we're going to drop in mid-development process. Blah, I knew I was going to goof that.
Yeah, mid-development on our solid-state monoblock, maybe, kind of amplifier. We'll talk about that a bit more in a bit.
But before we get into that, we should mention that over at valvesNmore, we're in the last weekend of the Black Friday sale. And here's your chance to grab a 15% store discount on the entire store. Everything in the store is 15% off. That's over in the tube side, not on the kit amp side. The kit amp side had its fall sale already, which was an amazing success. And the first weekend actually for the tube sale in valvesNmore, we were just about knocked off our feet. It was just so busy. And we had a couple of really big orders, which kept us busy. Anyways, a big thank you to everybody who participated. It's always good to have to be handing out discounts and bring some cash in so that we can actually do development work and bring in more tubes.
Yeah, and to share some great tubes with the world out there, and hopefully everybody is enjoying them right now, listening to some great music.
So the last day for the sale is Sunday at midnight, but many of you probably know I always sneak an extra day in for those that just, for some reason, they just can't get their act together until the last day, and then they miss it. I always get emails on the Monday morning saying,
is it over?
I had planned on buying a whole bunch of tubes. So anyways, but before we get into this, caution everyone, tube amplifiers and electronics can have very high voltages present, which can be lethal. Exercise extreme caution when working around them. Always consult a professional technician when in doubt. So this is version 1001. No, not really, but it is the platform in which we've been working away on our, what we hope will be our new kit amp, which will be a pure Class A, solid state, monoblock probably, but we're thinking about different configurations. We're thinking maybe we can design a chassis in which you can have half the power and a stereo amplifier and parallel the circuit and have a much more powerful monoblock. And yeah, so
yeah, we're not sure yet. Still kind of early days on that, but we'll see what we get out of it.
Yeah, I mean, power always sells, but with pure Class A, the big problem with power is heat.
Yeah, efficiency.
Yeah, well, or is lack thereof of efficiency. So the vast majority of all that goodness that you're generating is essentially to clean up the power supply and create an extremely low noise source of power, and so the output devices are running clean, and that's actually where we're at. We had, and it's kind of funny, we initially had a noise issue without plugging in the balance preamp, which is the driving preamp, and when we plugged in the preamp, we had a much lower noise floor. And then we fixed that problem, and now
it's inverted.
Now it's inverted. Now, with nothing plugged in, the amp's very quiet. It's not quite there, but it's almost there. I think we're at 3 millivolts in idle, which is not a heck of a lot. But if we plug in the driving preamp, it comes all the way up to 10.5 millivolts, which is too much. You can actually hear that from the listening position.
So it's still in active development. We're still sorting out the bugs, and we're still learning on it, because this is something that we haven't developed before, and it's very different from a lot of topologies out there, and we're hoping it's going to be something unique and very good sounding.
Yeah. Now, what makes it different? Well, besides the fact that it's built on a nice big chunk of plywood, well, I mean, the reason why it's built like this is because it gives us an incredible amount of flexibility. If we were to stick this into a chassis, we'd have to go into the chassis, open the chassis up. We might not have enough room, But
And to be fair, on some of our tube designs, we do absolutely do that because we have those parts around and they're designed to be prototyped with. But with this being such a new design, it's better to build it open like this.
yeah. So now I guess we should run over just quickly the stages so that people can sort of understand what they're looking at.
Yeah.
And it all starts off with an IEC with the power source.
Yeah, you might not be able to see it in the back here, but this is where you plug in.
You can see a lot of yellow-green wires coming back to it. Those are our ground return paths. There's another star ground down here. Here we've got a toroidal transformer. And because this particular prototype is a true balanced monoblock, it's got two power supplies essentially. Mm-hmm. So we've got a positive phase and a negative phase.
Or positive DC and negative DC supply.
Yeah. And we have a positive and a negative filter array or stages, because I think we're up to 7 stages of filtration.
In total, yeah.
In total. And then over here, this little module here sets the operating point. So there's a little bias circuit for the positive and negative side of the amp. And over here is a fairly large heatsink, given that we only have 2 MOSFETs bolted down to it. Mm-hmm. So, yeah. And
there really isn't a whole lot to it, and that's how we like to build our stuff, if possible.
Yeah. Now, you might think you're designing a single-stage monoblock. Does that not make it easier? Mm-hmm. Well, actually, when you remove stages in a preamp or a power amp like this, it actually makes it harder in general. It makes it easier to get great sound. And we already know that this sounds very good. We're really quite impressed when we can actually hear the music and not the noise that it's generating. It's generating 120 hertz clean, which is really unusual. Normally, you'll see the noise floor of an amp go all the way down to maybe 10 hertz and all the way up to 250 or 60 hertz, with a couple of blips at 60 hertz, 120 hertz.
Yeah, you'll see some overlapping harmonics and things from, 60 hertz from the wall, 120 hertz from the rectification, and then multiples of those. But no, this is surprisingly clean.
Yeah, so we have a noise at 120 hertz, mm-hmm. Which tells us one thing pretty quickly, and that tells us that it's after the rectification, because before the rectification, depending on the cycles that your AC mains are running at, 50 or 60, in our case it's 60 hertz, when you rectify that AC and turn it into DC, you double the frequency. So we go from 60 hertz to 120 hertz. So we know that the noise is in here somewhere, mm-hmm. Or in the preceding stage even. And so it's a lot of fun doing development work. Now, would we just slap ideas onto this design and see if they work? Sometimes.
Yeah, sometimes.
But what we really prefer to do is we start off with the basic concept. We knew we wanted a solid-state monoblock. We knew we wanted to drive it with tubes. That was a no-brainer. And in the first version of this build, which is on a completely different chassis, we had 3 stages. We had a gain stage, we had a driver phase stage, and then we had an output stage. And that's quite common for solid-state amps. Mm-hmm. But these days they can be 4 stages, they can be 5 stages. In modern gear, it's insane. I think a gentleman who was looking for, I think a tube to help the sound of his amp, he had an integrated amp, and we brought up the pictures of the amp and the data sheet, and this thing looked like you could have easily piloted a spaceship across the galaxy. It was incredibly complex.
Took integrated to a whole new level. I think they fit a kitchen sink in there somewhere.
Yeah. Well, there were so many electronics, if there was a sink in there, you wouldn't be able to see it. It was insane. And I thought, how good could that possibly sound? The signal path is going to be going this way and through this device and that device. And that was what we discovered when we built version 1 of this, was that 3 stages of solid state transistors muddied the sound and gave it kind of an edge especially in the treble, that I think a lot of people who maybe grew up with solid state gear sort of got used to. But we've lived with tube gear for a long, long time, and tube gear does not have an edge in the treble, and it tends to have a nice bit of warmth in the mid-range. That can vary, but you would almost never talk about any sort of vintage preamp or power tube as being edgy in the mid-range. There are some modern preamp tubes that are. And we have no idea why. It's like they took the worst of solid state technology and stuck it in a vacuum tube, which makes no sense, but you know.
It is what it is.
It is what it is. So we got rid of 2 stages, and right away, even though we had in our first version of this build, we had a much higher noise floor. We could hear right away that the mid-range had a nice touch of warmth, just a touch, but enough that it wasn't sounding solid statey. Is that a word?
I think so. Well, if it isn't, it is now.
But the main thing is, and Charles is really sensitive to this, you do not like edge up in the treble, do you?
The edge in the treble drives me crazy. I can't listen to it for more than a couple of minutes.
Yeah.
I just go nuts.
Yeah. And then I hear a squeak, make it stop!
Yeah.
So that disappeared completely when you got rid of those previous stages of transistor goodness, well, ungoodness. And so now we're at the point where we just have to quiet it down, and that's often the case when we work on, doesn't matter if we're working on an OTL kit headphone amp or a new preamp. In fact, we had a similar problem with our balanced preamp. The noise floor was a little bit too high, and we had to put some work into it and get it down even more. And that is pretty typical. The one disadvantage to working with an open chassis like this is that there is no shielding.
Yeah, and the wire management is a little bit haphazard, as you can probably tell.
Well, I don't know. I mean, I put hours into,
it's safe, but it's not ideal.
Sculpting the position of every resistor. And I did loop the ground return path right over the top of the noise.
Yeah.
With no shielding.
Yeah, that helps.
But seriously, we know through experimenting that some things, like the 0-volt return path, so long as the gauge is good enough to carry all the current, really doesn't affect the noise floor that much. But it is a bit of a disadvantage. So we always estimate that we're going to get a small advantage by going into a shielded chassis. But in reality, we often actually increase the noise floor slightly. And we're not really certain why that is, but that just seems to be the case. Maybe it's because components get crowded. In a prototype build, you tend to have a lot more space, and in a chassis, you tend to get crowded. Okay, now back to what we were talking about.
Yeah.
Development work. So if we mostly don't just slap things into the design hoping that they'll work, how do we make changes? Well, we collect data off the first version, first of all. So we document the voltages, we document the noise floor. If it's safe to put in system, we'll put it in system almost right away and start listening to it.
And we try to make sure we have a good understanding of how everything is functioning, and if there are problems, where those problems are being generated from.
Yeah. Now, once we've got all that data, we also at the same time will have a computer model of this whole thing working. And if applicable, we'll have the previous or post stages also plugged into the model. And that computer model has advantages and disadvantages. The big advantage is that if there's a critical error in the circuit design, it'll tell us.
Yeah.
And it will just simply refuse to run. And it'll send up a nice big flashing red light saying, you know, unplug, unplug. No. What is it?
No, it just pops up and gives you can't run because of such and such reason error.
Yeah. A fault in transistor 125.
Hopefully we don't have 125 transistors.
Yeah. No, but that amp we were talking about earlier does. Probably.
But yeah, it's the simulations are really useful for a number of different things. Another disadvantage that they have, though, is that they are ideal. So just like how this is not an ideal setup, the simulation is assuming that everything is exactly on spec, that there's no noise coming in from the outside, that the ground paths are perfect. That
the resistor parallel groupings are perfect values of half an ohm, which they never are.
Yeah. Now we can go in there and we can mess with those intentionally to try and add some variance to it, and we sometimes do that. But what it's really good for is doing things like building filter networks and power supply simulations. Those are all really good, and for estimating our maximum power output. That's usually very close to what we actually get in reality, and it's just very handy for that. So while we're talking here, I'm going to pop up a short video on the screen, and you can see the simulation for this amp exactly as it is right now, running.
Now, I should drop a caution before we bring up the simulation. Don't build the version that you're seeing in the simulation. It's still not a complete design. It doesn't have any of the safety features that will have to be incorporated eventually in the amp. It's just the core concept of the prototype functioning, and it will change over time as the development work continues.
And you can actually see the current flowing through it in different directions. This is actually not conventional current flow. This is real current flow, so it's the inverse of what you're expecting. We find that's just more useful to look at it that way.
So this is the actual electron flow.
Yeah. So this is electrons flowing from the negative to the positive, not the reverse of that. And you can see we've got our filter stages, we've got all of our big caps, we've got our half ohm resistors, which in reality are actually paralleled 1 ohms, and we've got our little 4 ohm power resistor off to the side here. So it's really handy because we can very quickly make changes to the simulation and see what happens before we go through the trouble of soldering in and changing things on the actual prototype.
Okay, what did you think about the simulation? That was pretty cool, eh?
Yeah, it's a great tool. I especially love being able to see the current as it's moving through the circuit in real time. It's really neat.
That's a very useful aspect of it as well, especially, you know, once the basic circuit is working and sounding great, if we have a small problem that has to be eliminated, we can sort of zero in at the simulation level and get a clue as to what's going on, particularly following the current flow. That's an extremely useful thing. What's the software called that we're using, Charles?
Yeah, so it's based off of LT Spice, which I'm sure a lot of you already have heard of because it's one of the major electronic simulation softwares out there. But this is specifically called Falstad, F-A-L-S-T-A-D. We'll put a link in the description down below for it. And it's useful for simulating all sorts of circuits. They actually have models in there for basic tryouts as well, and we use those in some of our other simulations too. So go ahead and check it out and have some fun with it.
Yeah. Now, where are we going to go next with this design? Well, we have a couple of ideas. In fact, it'll be as soon as this video is in the can, or should I say on the silicon, to be precise. I'm going to bring it back into my lab. This is actually my project. I couldn't do it without Charles's help, but I'm the lead on this, which means I build, I modify, I blow it up. Well, actually, we haven't blown this one up yet.
Yeah.
And I think it's something to, it's something to definitely avoid. I think that's a good thing, actually. And I'm going to make a single modification that I have in mind to see if we catch our 120 hertz monster noise and our gremlin, and
then we'll come back and we'll test it and see if that fixes it.
Yeah.
And this is how our development process goes, and this should be the same for everybody here. Change one thing at a time and test it.
Document it.
Yeah.
And both in your actual, we have a working schematic. Charles has a working computer model. And then we have a physical build. So we document the change. We'll often check it in the model to see if it's going to cause any problems, or if it shows some promise. And then we'll physically put it in here, document that, and then once we've got it up and running on the bench and nothing's blowing up, no smoke, then we put it in the system and
see how it works there.
Yeah. So, and often what happens is when you're trying to catch a problem, you catch some of it. It's like catching, we've got a lot of little lizards that live around our place. In fact, we have thousands of little lizards. We're the lizard capital of our city. And, you catch one of those little buggers by the tail, well, you'll end up with a little stub of tail, and the lizard will say, "See ya." Not that we would ever do something like that. But there's lots of kids around here who like to play with the lizards as well. And so you catch some of your problem, or you get perhaps an insight into the problem, and then you're left with the remnants. So you have to go and
iterate again, try something else, and see if you can catch the rest of it. And this is what development process is. You come up with an idea, you test it, and then you go back to the drawing board and you fix the issues with it, if you can.
At the end of the day, our goal is to bring a practical, affordable, great sounding piece of audio gear to you as a kit. We actually have a shelf of duds not far from where my shoulder is here, and you'll never see the duds. But I would say about 2/3 of the time, maybe half the time, when we start on an idea for development work, something substantially good comes out of that. So it's not always doom and gloom.
Even with the duds, we learn something useful.
Yeah, like don't design on that idea again.
This is a dead end. Don't go there.
Yeah, or sometimes it's just this is not practical, or this is not the best idea in the world. It seemed like a good idea when you start, but anyways, so we'll probably drop in once or twice more. Maybe the next time you see this, it'll actually be working, and then we'll start sharing the circuit with you. I shouldn't say working. What I should say is
working better.
Working at 100% or 99.9% or however you want to look at it. Right now, I would say the circuit is working at about 90 to 95% there. It's almost done.
Yeah.
It's very, very close.
It's got a lot of good things going for it. We just have to fix that one little issue.
Yeah. Okay. This is Jim.
And Charles.
Signing off. Cheers, everyone.